Welcome to another lesson in vector calculus. Today's topic is all about line integrals. Line integrals are kind of a combination between single integration and multiple integration, as we'll see as we get through all the material. In order to talk about line integrals, we'll start out with the definition of a line integral. What is a line integral and how do we make it happen? Then we'll have examples on how to calculate line integrals. And then we'll get into the main application of line integrals, and that comes from physics, and that application is on work. And then finally, I'll show you another notation that will give us line integrals also, and that notation is called differential form. So let's start out with the idea of a line integral. So here I have a curve. It's one of my favorites. It's a spiral. So instead of just thinking of this as just a curve, let's think of this as a wire. So now it's a physical object. But let's get a little more complicated. And let's suppose that along this wire, the density of the wire is changing. So it might be really heavy over here and then lighten up, then get heavy again, and maybe mid-sized and heavy and lighten, etc. And we want to find out the weight of this wire. So you can't just find the length of it and multiply by density because we don't have a constant density. So instead what we do is we take our cue from all the rest of the subjects on integration. So we cut up the wire into little pieces. I'm going to focus on this one little piece. So here we have a piece of a wire. And as long as we cut it up into small enough pieces, we can say that this little piece is approximately a line segment, and that the density is approximately a constant. So in everything we do in this class, our density function will be continuous, so we can actually say that the density is approximately a constant if you cut it up into little pieces. So in that case, the weight of this little piece will be the density of the wire times the length of that little piece. The density we'll call f of xy. The length is L. But then by the Pythagorean theorem, the length of the wire is the square root of the sum of squares of the changes in x and the changes in y. So what we can say is that the weight of this little piece is approximately equal to f of xy times the square root of delta x squared plus delta y squared. Now we've seen before that taking one little piece is not enough. We need to look at all the little pieces and add them up. And that is the motivation behind the definition of a line integral, which says the following. Let C be a curve in R2, and let f of xy be a function. Then the line integral of f along C is defined by, we write down the integral over C. Notice we're not going from a number to another, we're just going on a curve, of f of xy ds. You could think of s as being a length element, and that is equal to the limit of the summation of f of xy times delta si, where delta si is the length of that little small piece of the curve. F of xy is the density function, or just some function, doesn't even have to be positive. Sigma is a summation. We're going to add up all the pieces, and we're going to take a limit as the length of the pieces all go to 0. You could also talk about the line integral in 3 dimensions. And as you can guess, it really isn't any harder. We just have to have a function of 3 variables instead of a function of 2 variables. And what it says is that the line integral over a curve C of a density function of three variables, f of x, y, z, ds is equal to the limit of the summation of f of x, y, z, delta si. So now let's realize, just like in everything else we do with integration, these summation definitions are great in understanding concepts, but they're not very helpful at all in terms of actually solving integration problems. So there's another way of finding a line integral, and that is when we have either a vector valued function or a parameterized curve. Those are basically the same thing. So let's suppose we have a vector valued function, r of t, equals x of t, comma y of t. Then we know that ds is equal to the magnitude of r prime of t dt. We've seen that before. R prime of t gives you the length of that curve, or at least a little tiny piece of the curve. And if you multiply by delta t, we'll take a limit to dt. That truly gives you that little ds element. And the magnitude of r prime of t is the square root of x prime of t squared plus y prime of t squared. And then we still have the dt. And that leads us to the result that the line integral over a curve C of f of x, y ds is equal to the integral from t0 to t1, that's the starting point for t and the ending point for t, of f of x of t, comma y of t, so instead of xy, we have x of t, y of t, times the magnitude of r prime of t, dt. And that gives us a much easier way to find line integrals, because now we could just do a regular old single integral. Although, you got to be careful about what easy is. Because remember that r prime of t in magnitude is the square root of a sum of squares. And if you take a square root of a sum of squares, multiply it by some other big old function of t, integrating that is often going to be impossible to do in closed form. So often, we're going to be doing these general line integrals using technology. Let's look at an example. So let's see if we can compute the line integral over the curve C of x squared y ds, where C is a curve defined by y equals 2x squared minus x cubed. X goes from 0 to 2. So this curve looks like this. We're going to start at 0. We're going to end at 2. Kind of goes up and down. And it turns out that when we have line integrals, the direction matters. Because if we go backwards, we'll end up from 2 to 0, and we'll end up with a negative answer of what we would get if we went forwards. So always pay attention to the direction at which we're moving along the curve. So let's work this out. So the first thing I need to do is parameterize this curve. But since we have a curve defined as a function of y in terms of x, the way to do that is we let x equal t, and then y is just a function of t. So 2t squared minus t cubed. And that gives us the parameterization of this curve. And t goes from 0 to 2 because t is just x. So now I can start plugging in. So we have an integral from 0 to 2, because x goes from 0 to 2, or t goes from 0 to 2. We have an x squared, x is t, so x squared is t squared, times y is 2t squared minus t cubed, so we multiply by 2t squared minus t cubed, and then times the square root of the sum of the squares of r prime. Well, the derivative of t is 1. 1 squared is 1. the derivative of 2t squared minus t cubed is 4t minus 3t squared. So we have 4t minus 3t squared, quantity squared. All that is under the square root times dt. Try as you might, you can do everything you could trying to get techniques of integration, but you will fail miserably. This integral is not solvable using any kind of closed form technique. You can always use power series, but that's not closed form. So instead, when you have something that's this hard, it makes it easy because we have no choice but to use a computer. So I used my computer, and I got that this integral is about 3.57. So we could say that the line integral over c of x squared y ds is about equal to 3.57. Now let's compute a line integral in R3. So the question states, find the line integral over the curve c of xz ds, where c is a circle of radius 2, centered at the point -2, 1, 3, parallel to the yz plane. So what we have is a circle. If this is the x-axis, then our circle looks like this over here. So notice that the x-coordinate of the circle is a constant -2. That's what it means to be parallel to the yz plane. -2 because that's the center, and if the x-coordinate of the center is -2, then every point on the circle must have x-coordinate -2 for it to be parallel to the xz plane. So that gives us the way of finding a vector-valued function for this circle. We let x of t equal -2, and then for y and z, we realize we have a circle. The center is 1, 3, so we have 1 plus, the radius is 2, so 2 times the cosine of t is going to be the y component. And then for the z component, our center is 3, so we have 3 plus, the radius is 2 times the sine of t. So there's a vector-valued function that represents this circle. We can compute the derivative, r prime of t, is the vector 0. The derivative of -2 is 0. The derivative of 1 plus 2 cosine t is just -2 sine t. And the derivative of 3 plus 2 sine t is 2 cosine t. We can put all this together, and we can find the line integral. Since it's a circle, we're going from t equals 0 to t equals 2 pi. We have x is equal to -2, so we have -2, times z is 3 plus 2 sine of t, so here's a 3 plus 2 sine of t, times the magnitude of r prime. Well, 0 squared is 0, -2 sine t squared is 4 sine squared t, and 2 cosine of t quantity squared is 4 cosine squared t. But take a look at this. 4 sine squared t plus 4 cosine squared t is just 4, and the square root of 4 is 2. We could say 2 times -2 is -4, and we could bring that outside. And what I get is that this line integral now equals -4 times the integral from 0 to 2 pi of 3 plus 2 sine of t dt. And this now is a very simple integral. The integral of 3 is just 3t from 0 to 2 pi gives you 6 pi. 6 pi times -4 is -24 pi. And the integral of 2 sine of t from 0 to 2 pi just gives you 0, because you end up with a -2 cosine t, and it's from 0 to 2 pi, and they cancel each other out. So I'm left with that this line integral over c of xz ds is negative 24 pi. So now let's use line integrals. I want to get into work. Work is a very important physical quantity that comes up a lot. Anytime you're dealing with electromagnetism, we talk about work as you're moving an electron through a wire. If you're talking about going from one place in space to another against gravity, you want to talk about the work that it takes to go against gravity. There are many, many, many types of physics problems that involve work. So in particular, work is equal to F dot dr, force times distance. And that's equal to F dot t ds. So then t, if you remember, was r prime of t over the magnitude of r prime of t, because t is a unit tangent vector. That was our definition. The great thing about this is ds is the magnitude of r prime of t dt, and if you multiply t times df, the magnitude of r primes cancel. So what we're left with is that the work is the line integral over c of f dot dr, which is equal to the integral from t naught to t1 of f, that's the force function, of x of t, comma y of t, times r prime of t dt. You don't need magnitudes because they cancel. So now let's look at an example. Let's suppose we have an electron and it moves along a wire in the shape of a triangle with ordered vertices 1, 0, 0, 1, and 1, 1. Let's find the work done if the electron moves around the entire triangle against a force, F of xy, equal yi plus xj. Let's draw a little picture. We have this beautiful triangle. We're starting at 1, 0. We're moving over to 0, 1. Then we're moving over to 1, 1. And then we're moving down back to 1, 0 to complete the triangle. The first thing we want to do is parameterize these three line segments. So the first one, since it's going from 1, 0 to 0, 1, 1, 0 gives you a 1 and then a 0, and then we're moving to 0, 1, so that means that we're rising in the x direction, negative 1, because we're going backwards, we're going left, so there's our negative 1 times t, and we're rising in the y direction, positive 1, so there's our positive 1 times t. For the second line segment, we're starting at the point 0, 1, so we have a 0 and a 1, and then we're rising in the x direction 1, because we're going 1 across, so that gives you a 1t for the x coordinate. And then we are not rising at all in the y direction, so then we have a 0t for the y component. That gives us t, 1. Then for the third vector, we're starting at the point 1, 1, so our constants are 1, 1. The x coordinate isn't changing at all. We're not moving horizontally, so we have a plus 0t. I can leave that out. The y coordinate is going down by 1, so that means a minus 1 times t. And there's our parameterized curves. Because we have three separate parameterized curves, we expect to have three separate integrals. So the first integral goes from 0 to 1 of, and then we have y. Y was t, so there's our t. And we have x for the j component. X was 1 minus t, so here's 1 minus t for the j component. R prime is negative 1, 1. So there's our dot negative 1, 1 dt. Then we're going to have plus Now we have to find the work done as we move along the second line segment. So in this case, y is equal to 1. There's our 1. And x is equal to t. There's our t. And then the derivative of the vector value function t1 is 1, 0, tt. So now let's find the work done as we move along this final curve. So again, y is equal to 1 minus t. So there's 1 minus t. X is equal to 1. There's the 1. We have r prime is 0, comma, negative 1. There's 0, comma, negative 1. We dot these two vectors and multiply by dt. So the good news is that each of these integrals all go from 0 to 1, so I can combine them. So let's take the dot product of the first guys. We have a negative t plus a 1 minus t. That's a 1 minus 2t. Then the next one, we have a 1 plus a 0. That's plus 1. And then the third one, we have a 1 minus t times 0. That's 0. Plus 1 times negative 1. That's a negative 1. So there we have it. We just have a regular old single integral from 0 to 1 of 1 minus 2t. And then plus 1 minus 1. Those cancel, of course. So then we find the integral from 0 to 1 of 1 minus 2t dt. And that's an easy integral. I could do that in my head. I could write it down. I could use technology, but I don't really need to. I just get 0. And that's important. So that means the work done moving around this triangle is 0, if this is the force. Later we'll understand how to do this without doing any significant work at all. That is a pun, by the way, doing any work. But not today. We don't have the fundamental theorem of line integrals yet, but we will get that. So now let's do one more example of work, but let's do work in 3 dimensions. So the question states, find the work done by the force F equals the vector field z, comma, xy, comma, 3z to move a particle from the point 2, negative 1, 4 to the point 1, 3, 5. It doesn't say this, but we're going to assume that when we say we're moving it from point to point, we're going to move it along a line segment. So we want to move the particle along the line segment between these 2 points. So as usual, we're going to start out with finding the parameterized curve. We start with 2, negative 1, 4. Here's the 2. Here's the negative 1. Here's the 4. And then we compute the 3 slopes. 1 minus 2 is negative 1. So we have minus 1t. 3 minus negative 1 is 4. So we have plus 4t. And 5 minus 4 is 1. So we have plus 1t. We can compute our prime of t, which is just the vector valued function of the slopes. Negative 1, comma 4, comma 1. We could put all this together and find that the f dot r prime of t is z times negative 1 plus 4 times xy plus 3z times 1. So z times negative 1 plus 3z times 1 is 2z. And then we still had the 4 times xy. So we get 2z plus 4xy. Z is 4 plus t. X is 2 minus t. And y is negative 1 plus 4t. So this is a matter of foiling all of that out, adding up the 2z, or the 2 times 4 plus t, combining like terms. And what I got, I'm going to spare you the algebra, you can work it out if you're interested, was that this is equal to negative 16t squared plus 38t. So now we can write this as an integral. It goes from 0 to 1 of the negative 16t squared plus 38t dt. This is an easy integral. and it's just 41 over 3. And that's all there is to finding work in R3. As you might have noticed, the integration typically is a lot easier to find work done than it is to find a general line integral. The last thing I want to talk about is differential notation. And it says the following. We can think of dr dt times dt is equal to dx over dt dt I plus dy over dt dtj plus dz over dt dtk. And now I know they're not fractions, but we can kind of think of them. We can cancel. And we get that this is equal to dxi plus dyj plus dzk. And then we can look at having a vector field f equals mi plus nj plus pk, and then taking f dot r prime of t dt. So that just says we take the dot product of dxi plus dyj plus dzk and mi plus nj plus pk, and that's actually quite simple. You just get m dx plus n dy plus p dz. I actually didn't do anything here. All I did was define a new notation. But this notation is useful. So now let's use it. So the question states, find the line integral over the curve C of z dy plus x dz. So now notice that this is in differential notation, where C is a curve, r of t, equals cosine of t, comma sine of t, comma t, for t going between 0 and 2 pi. You may recognize this particular vector valued function. It's a helix. We have our circle, but then it's moving up as time changes. So let's work this out. We can say that f now is 0 because there is no dx component, comma z because that's the dy component, comma x because that's the dz component. R prime, just take a little derivative, is just negative the sine of t, comma cosine of t, comma 1. Now to find this line integral, we just take the integral from 0 to 2 pi, and we take the dot product. So that's going to be 0 times negative sine of t, that just goes away. We have z, which was t, times the cosine of t, so there's t times cosine of t, plus x, which is cosine of t, times 1, which is plus cosine of t, and then dt. This integral, it's a little more difficult, but it's not that hard. The cosine of t is very easy. The integral of the cosine of t is the sine of t. Sine of t from 0 to 2 pi is just 0. So that whole part goes away. So I just want to integrate t times the cosine of t. So I'm not going to go through all the details, but I want to remind you to integrate this. You use integration by parts. And then the bottom line is when you work out this full line integral, you end up with 0. So that's about all I have to say about line integrals. I hope this made sense to you. If not, please come to me, ask me some questions. Or if you have another instructor, ask your instructor questions. I'm sure your instructor will be happy to help. And have a wonderful morning or day or night. And thank you for watching this video.